gains. So yeah, this the MIMO system will give you minimum of NT comma NR. So so if you have a NT transmit antenna, and if you have a NR receive antenna, so there is a performance degree of freedom gain is min NT comma NR. Okay, so this is the degree of freedom gain or spatial multiplexing gain. So this plot shows the capacity versus SNR. I explained to you this curve is for the CISO case, single input, single output system. At 20 dB SNR, it is giving you 5. If you go here, and if you see, it will give you, for the single input, single output system, give 5 bits per second per hertz. But the MIMO system with the 4 transmit antenna and 4 receive antenna is giving you 20 bits per second per hertz. So there are 4 times capacity improvement for given signal noise ratio. That 4 times is the min of NT comma NR. Okay, so that's the capacity improvement. For in this case, single input and multiple output case, we are getting a capacity improvement that is due to the beamforming gain rather than the multiplexing gain. Okay, for the CISO single input and multiple output system, the degree of freedom gain is going to be only 1. So this side of the plot is showing again NT comma NR is 8 antenna. So you can see there is a 8 time capacity improvement at 20 dB SNR. So if you go here, you will see 5 into 8, 40 bits per second per hertz. So the degree of freedom gain is minimum of NT comma NR. So we saw this one, and we also show the slope of the high SNR slope. This is the region for high SNR. The high SNR slope also will give you the degree of freedom gain. Okay, so here is the high SNR slope is 4, and here is the high SNR slope is 8. And we also saw last class, end of the class, in the low SNR regime, the MIMO and the CMO will perform almost same here. So we don't need, if the system is operating at the low SNR regime, we don't need a MIMO system. We can use CMO system to get the performance enhancement. So we get NR-fold power gain in the case of CMO system. So we saw this slide as well, nature of the performance gain. At high SNR, degree of freedom limited, min NT comma NR fold, degree of freedom gain for MIMO gain, and the MIMO is crucial. For the low SNR, NR fold power gain only need multiple receive antenna. Okay, at all SNR, min NT comma NR fold gain due to combination of both effect, power gain and degree of freedom gain. So then we look at this slide at the end of the class. So the capacity is the channel capacity is the one showing how much gain, capacity gain that we will get from the MIMO system. But how to realize that capacity is the one we are going to see today. How to realize that capacity. It's saying for the 4 transmit antenna and 4 receive antenna, we can get 20 bits per second per hertz at 20 dB SNR. So how do we get that 20 bits per second. So that's the thing we are going to see today, which is the architecture that achieved that capacity for the fast fading channel. So again, we are going to consider fast fading channel and the slow fading channel, okay? So the fast fading channel, the architecture is called V-BLAS architecture, vertical Bell Laboratory layer space-time architecture. So you have a, data stream, independent data streams are coded using turbo code or LDPC code, and it is going to be transmitted through these channels. So these streams are add together, you receive the signal, your received signal is going to be summation of, k is equal to 1 to nt hk, something like that, okay? So you will get all the streams are add together, you receive all the streams are add together at the receiver. You need to decode each of the stream independently without the interference. So the receiver, all the streams are add together, interfere each other, and we need to decode each of these stream without the interference. So we can use the receiver architecture we can use maximum likelihood ML, maximum likelihood estimator, but this is the nonlinear estimator and very complex to implement. Then we can use linear receivers. This is nonlinear, linear receiver, zero forcing architecture, or MMSE architecture, minimum mean square architecture. These two are linear receiver, can perform, but it won't achieve the capacity, okay? It won't achieve, for example, if you have a 4 transmit NR and 4 receive NR at 20 dB SNR, it won't give you 20 bits per second per hertz that capacity is promised. So these, I will show you. We can use a linear receiver. The linear receivers are zero forcing and MMSE receiver. They can decode the stream, independent stream, but they won't achieve the capacity, okay? But there is a nonlinear receiver called MMSE, successive interference cancellation, that will achieve the capacity. So that's what the story today at the beginning, okay? So the slide is saying, can get the performance gain by sending independent coded stream at each of the transmit antenna and jointly ML decoding. Yes, we can able to get the capacity. So why it's surprising? Because the signals received add together, interfere each other. So to get the receiver, come up with a receiver that decode this interfered signal is, is a demanding task. So question is how to get the degree of freedom gain even when the stream interfere with each other. Okay, so because all these streams will be interfere at the receiver, so are we able to get the capacity? So that's the surprising results. Okay, so now I'm going to talk about zero forcing receiver. As I said, zero forcing receiver have a few names. People say interferent nulling, zero forcing receiver, and decorrelator. All are same thing, okay? Okay, so zero forcing have a 3 name: decorrelator, zero forcing, and interferent nulling. So all are same thing for zero forcing. So let's focus on the transmit antenna 1. So let's focus on this signal. So only this signal we are going to estimate. So the receive signal can be written as H1X plus this is the rest of the interference plus noise. So I hope you understand that equation. So the H1 is the channel between, this is a vector channel. Okay, so let's say the H1 is, H1 here is a vector contain, this is H11, we call H21, HNR1. So this H1 is H11, H21, HNR into 1. So this is the H1, okay? So the receive signal can be written as that form, okay? So receive signal Y is equal to H1, this is the H1, and this is the X1, plus the remaining signal. Remaining signal, here, these are the remaining signal. So when you are decoding at the receiver, all add together like this, okay? But when you are decoding this signal, these guises are, all these rest of the guises are going to interfere. Yeah, so when you decode this signal, all other signal will interfere. So all other remaining signal, this stream up to this NR stream, they are denoted here. These are interference. These are interference. So we are going to estimate only X1, but these guys are interference and plus noise. So this is the same equation as before. So Y is equal to Hx plus noise is the one, our normal MIMO channel equation. Okay, so this is NR into 1, and this guy is NR into NT, and this guy is NT into 1 vector, and this guy is NR into 1. So this equation, we can write it as a summation of HK, XK, and K goes from 1 to NT plus noise. We can write it like this matrix equation like this. And then we can write, consider we are taking, estimating the first stream. So we can write H1, X1, and then summation HK, XK, K not equal to 1 because we put the K here already, plus W. So we can write this equation, this equation, this equation. We can write it like that. So that's what is written here. Okay. So now, so we wanted to estimate this guy as X1 and treat all these guys as interference. So simple strategy is to null out the interference from other antennas. So let's consider we have only 2 antennas, but it can extend to more antennas as well. Okay, so this is the H1 channel. Okay, this is the H1 channel, H1, and this is H2. So consider only 2 transmit antenna, only 2 transmit antenna. So H1 is this guy, this vector, and this is the H2. Okay, consider only 2 antenna. So your receive signal is here. Okay, your receive signal is here. What you do is you project the receive signal orthogonal to H2. Okay, you project the receive signal Y orthogonal to H2, and you get this signal. Okay, this signal, and from this signal you estimate X1. Once you project that orthogonally, your interference is null, and then from this signal you estimate the X1. So this is called this is the concept for zero forcing or interference nulling or decorrelator. Okay, but you will lose some signal to noise ratio because this signal is bigger. When you project it, you have a smaller signal. from smaller, you will lose some energy in the zero forcing case. Okay, so that will come in a minute. Okay. So simple strategy is null out the interference from other antennas. So you project the receive signal orthogonal to H2. This is the interference orthogonal to that. Then your interference is gone. So you work from this signal to estimate X1. So, this is the receive architecture for bank of decorrelator. So as I said, decorrelator, zero forcing, interference nulls are all same. Okay. So you have a receive and a signal here. So this interference nulling, projecting this signal and then extracting this X1 can be done by this equation here. This is the zero forcing receiver. So this equation will do projection and also estimation as well. So, the receiver for the zero forcing receiver is going to be look like that. Your receive signal is here. All the transmitted stream are estimated by multiplying H into H Hermitian into H, inverse into H Hermitian. This is the receive signal. Okay, so the receive estimation. This is the NT into 1 is going to give by H Hermitian H inverse H Hermitian Y. Okay, so again you will see. So this is all the streams are estimated using projection, interference, cancellation, etc. Okay, so this is the concept of zero forcing. So for example, if you consider this matrix, this is the matrix. Okay, it have a NT transmit antenna. NT into NR dimension matrix. So if you take the first row of that matrix, okay, first row of the matrix, and multiply by the receive signal, then you will get the first stream. Okay, so what I'm saying is, if you from this matrix is NT into NR, you take the first row and multiply the receive signal, and you will get the first stream of this guy. And if you take the second row of this matrix and multiply the receive signal, you will get the second stream. So if you take the last row of this matrix, multiply the receive signal, you will get the NT stream as well. So this is the kind of a zero forcing receiver. Okay, any question? Okay, so zero forcing receiver is just receive signal into this matrix, okay, and you will get all the stream, okay. As I said, zero forcing receiver is not going to achieve a capacity. So here, the bank of decorrelator or zero forcing performance, you can see this is the bits per second per hertz, and this is the SNR. This plot is for NT transmit antenna 8, receive antenna 8, and IID relay fading channel. You can see this is the capacity of the channel capacity. This is the channel capacity. You know, if you see here, 20 dB, we will get 40 bits per second that we saw before as well. Now 20 dB, if you go here, it will give you 40 bits per second per hertz. This is the observation we got from the last few slides ago. Okay, so this is the channel capacity, but when you use the decorrelator or zero forcing receiver, what is the bits per second that you are getting is this guy. Okay, it is this guy. So you can see there is a performance gap between decorrelator and the channel capacity. So there is a performance gap, but there's one thing that you can notice. This slope and this slope are same. This slope and this slope are same. So that means the decorrelator achieve the the degree of freedom gain, but the capacity is not achieved. Okay, So that's one thing that you need to notice, that this high SNR slope are same. So you can see that's what is mentioned here. The decorrelator or the zero forcing achieve the full degree of freedom that min NT, NR of the MIMO channel because same SNR slope. Okay, that's what I said. The decorrelator achieve the degree of freedom gain at high SNR because the same slope are same, but there is a gap in the capacity. Okay, so that's what it's saying. But there is a still substantial constant gap at high SNR. The moderate and the low SNR, the performance is no good. Okay, so the decorrelator, even though it's achieved high SNR slope, it is not achieve the capacity. So that's the story about the zero forcing. So let's see how do we the next half an hour or so, we are going to see how to close this gap, and bring the receiver architecture that achieve the capacity. So that's the story. So this is interferent null versus match filtering. So we saw match filtering last time. So if you have a receive signal Y, H1, X1, and summation of HK, XK, K not equal to 1 plus W, then you can use a match filter that I explained to you last time. Match filter is what you do is you multiply the receive signal by H1 conjugate and divided by its magnitude. This is the match filter. So this is or maximum ratio combining. This kind of receiver also you can use as well. You receive signal is multiplied by H1 conjugate and divided by its magnitude. That's called match filter or MRC, maximum ratio combining. So we are now comparing interferent nulling, which is the zero forcing receiver, and the maximum ratio combining. So there's one more receiver here. Maximum likelihood, this is nonlinear receiver, zero forcing, and MRC, maximum ratio combining or match filter. So we are now comparing these two guys in this slide. So interferent nulling, remove all the interference at the expense of reducing the SNR. So I told you, when you project the signal, your SNR, you end up with dealing with a smaller receive signal, so your SNR is reduced. Okay, so that's what we saw here. You say, when you project the signal, when you project this bigger signal orthogonally to the interferent, you end up with this smaller signal, so that reduce the SNR. That's why your performance is bad. Okay, so that's what it's saying here. Interferent nulling, remove all the interferent at the expense of reducing the SNR. Match filter, project H1 into maximize the SNR, but SANR may be bad. So if you do maximum ratio combining or match filter, it will maximize the SNR, but it is not going to maximize the SANR. Okay, so the match filter will maximize the SNR. Okay, maximize the SNR, but it's not going to maximize the SANR. The MMSE we will see next few slides. This is the techniques maximizing the SANR. Okay. So match filter project, match filtering or maximum ratio combining project onto H1 to maximize the signal to noise ratio, but SANR may be bad. Okay, so here is the performance. So this plot is the y-axis. The y-axis is the capacity of the maximum ratio combining divided by the capacity of 8 transmit and 8 receive antenna. And also the capacity of the zero forcing divided by the capacity of 8 by 8. So there are two plots. the solid line is for the maximum ratio combining divided by the capacity of the 8x8 transmit antenna, 8 receive antenna case. And this guy, the dotted line is the capacity of the zero forcing divided by C 8x8, okay? So if these guys has achieved capacity, this will be 1, okay? This will be, that ratio will be 1. So that maximum is 1, okay? Because it's a normalized capacity in the y-axis. So you can see, you know, the merge filter performing very good at the low SNR regime. So low SNR regime, the merge filter is perform, or maximum ratio combining perform better, almost achieve the capacity because the maximum capacity over the channel capacity is 1 mean, it almost achieves the capacity at low SNR. But when SNR is high, its performance is degrading. Why is it? Because the maximum ratio combining is maximizing the signal to noise ratio. At low SNR, these interference between the streams are very less, okay? Because at the low SNR, the interference between the streams are very less because the maximum ratio combining is not cancel the interference, and interference is low, but is performing better. But when the signal to noise ratio is become higher, so these streams signal interference will be strong. The maximum ratio combining is not going to handle the interference, and its performance is less. Okay, and similarly, the decorrelator or the zero forcing normally cancel interference, but the low SNR it is there's no interference, but the receiver is built to cancel interference. So we are kind of applying a over conservative solution. So the performance is bad, but when the high SNR, the interference will be there between the stream. The zero forcing will cancel those interference and performance is better. Okay, so that's the message from this plot. So I'll repeat again. This is the maximum ratio combining. At low SNR, there's no interference between the stream or the less interference, and it will enhance the signal to noise ratio. Your performance is better, capacity performance is better. But when the SNR become high, the stream, these streams interfere each other, the maximum ratio combining is not built to cancel interference, so the performance is reducing. But the zero forcing at the low SNR, it will cancel interference, but there's no much interference, so we are kind of applying an over-conservative solution to the situation, so the performance is not good. But at high SNR, there's interference, so zero forcing will handle the interference very well, and performance is here. But here you can see the capacity. Ideally we should have one capacity. You can see there's a big gap here. Okay, back gap here. So how to remove this gap is the one we are going to see. We like to have a receiver that can achieve the capacity all the time, low SNR and high SNR regime. So that's the objective. So I will tell you that MMSE SIG will achieve capacity for low SNR and high SNR. It's going to be go like this, always one, okay? So optimum linear filter. So now we are going to look at the MMSE, minimum mean square error receiver. So this is the receive signal again, okay? So the receive signal can be written as this form, H1 into X1, and summation of the remaining interference plus W. Seek a linear filter that maximizes the output SANR. So the MMSE is maximize the signal to interference plus noise ratio. Maximum ratio combining, maximize the SNR, but MMSE receiver is going to maximize the signal to interference plus noise ratio. So seek a linear filter that maximizes the output signal to interference plus ratio at all SNR. Offer the optimum compromise between nulling. So this MMSE offers the optimum compromise between nulling and merge filtering. Okay, it whitening the interference first and then merge filter. This is the linear MMSE filter. Okay. So, for example, let's say consider this is the kind of a interference subspace, The decorrelator is projecting the received signal orthogonally to interference subspace. The optimum filter is somewhere here, and the merge filter is doing somewhere here. Okay? So high SNR, the MMSE achieved the decorrelator. At low SNR, MMSE achieved the merge filter. Okay? We saw in one of the previous slides, high SNR, the decorrelator is performing better. At the low SNR, the merge filter is performing better. That we saw it here. Remember this plot at low SNR, merge filter is performing better. At high SNR, the zero forcing performing better. The MMSE is going to achieve this performance at the low SNR and this performance at the high SNR. So that's what we are going to see. That's what is said here. The high SNR, MMSE achieved the decorrelator or the zero forcing. At the low SNR, MMSE achieved the merge filter. So here, that's what is shown here. So this is the same plot. As I said, this is the each of the capacity of the receiver divided by C, channel capacity C88. So this is the plot for the merge filter or the maximum ratio combining, and this is the plot for the zero forcing or interference nulling, and this is the MMSE receiver. Okay, you can see MMSE receive almost achieve the approach the merge filter performance at the low SNR. At high SNR, it achieved the zero forcing performance. So because it is designed to maximize the signal to interference plus noise ratio. Okay, so that is the MMSE receiver. Okay, MMSE receiver. But still, you can see there is a gap here. At low SNR, it's almost achieved the capacity because the ratio is 1. Okay, MMSE receiver achieve capacity because this is a MMSE receiver rate divided by the channel capacity. So if you achieve the capacity, mean this ratio become 1. Okay, so low SNR is achieving the capacity, but when the high SNR comes, there is a gap between the capacity. So how do we close this gap is the one we are going to show next, which is called MMSE 6, successive interference cancellation. So, this plot, MMSE improved the performance of the decorrelator at the moderate and the low SNR, does not remove the gap in the performance in high SNR. So that's what I said. MMSE doing a good job at the low SNR, but at high SNR, there is a gap here. So that's what is saying. Does not remove the gap in the high SNR, performance at high SNR. To remove the gap, we have to go to a nonlinear receiver. So these receivers, these three receivers are linear receivers. The zero forcing, maximum ratio combining, MMSE, these are all are linear receiver. Linear receiver mean easy to implement, the complexity is less. But this guy is a nonlinear receiver. This guy is a nonlinear receiver. Of course, this guy also nonlinear receiver. It is complex to implement. Okay, so to remove the gap, we had to go to nonlinear receiver. Okay, so this is the MMSE with the SIG receiver. Okay, this is the MMSE with the SIG receiver. So what this is doing is you have the receive signal here. You have a receive signal here. The MMSE receiver equation is very similar to the zero forcing equation, and you will have some additional term here. Some additional term. No, not like that. This is the kind of a MMSE receiver. Okay, so you take the this matrix. You take the first row and multiply the receive signal. You can decode the stream 1. You can decode the stream 1. Okay, then what you do is you estimate that stream receive signal, you subtract that interference. So you estimate one of the stream already. Normally, we estimate the strongest stream. The strongest stream from all of these mean which of the column of that H matrix have a strongest gain. Okay, you normally estimate the strongest stream. Let's, the strongest stream is estimated. And then why we need to estimate the strongest stream? Because strongest stream, when you estimate the strongest signal, other signal will be interfering. But the strongest signal, when you estimate the strongest signal, you will be estimating performance is better because it's a stronger signal. So anyway, so you first estimate the strongest stream, and then from the received signal, you subtract that stream, okay? So that's what is called successive interference cancellation. You subtract the received signal from the strongest stream, and then estimate the second strongest stream. You estimate the second strongest stream, and then subtract the second strongest stream from the received signal, and then you go further, and estimate all of the stream. So this is called MMSE successive interference cancellation. So every time you estimate the stream, you multiply your received signal with one of these row. Okay, when you multiply the first row with the received signal, you will estimate the stream 1. Then you second row receive signal and multiply the receive signal with the second row, you will estimate the second stream, and etc. So if you do a successive interference cancellation, you will achieve the capacity. So that's what is shown here. You can see here, this is again the capacity versus the rate of all of these receivers. Okay, rate of all of these receiver divided by the capacity. You can see MMSE SIG achieve the capacity. You see, it's always 1, 1, 1, 1, 1. And this is the MMSE receiver, and this is the match filter or the maximum ratio combining, and this is the zero forcing or interference nulling or decorrelator. And you can see the MMSE SIG achieve the capacity. Okay, how do we? So there is a proof in one of the tutorial question. If you want, we can do that proof. This is the capacity of the MIMO channel. This is the capacity of the MIMO channel. This is the MMSE signal to interference noise ratio, and we can prove why MMSE SIG which achieve the capacity. There is a nice proof. This is equality. This is not an easy proof. It's a very nice proof in one of the tutorial question. We can do if you want nowadays, isn't it? We can do that question. So why is MMSE SIG is optimum? We can prove this one, that is achieve the capacity. Okay, MMSE is information lossless at each stage. And the successive interference cancellation architecture implement the chain rule of information. This is the chain rule of information. That's why it's optima. MMSE SIG is optimum. Any question? That's what we show here. The MMSE SIG is the best one. It's achieve the capacity. You see. This is the ratio of the MMSE SIG capacity divided by the channel capacity. So if it is 1, it's achieve the capacity. And MMSE is the second performance better. But here is as I said, it's a nonlinear receiver. We need to do successive interference cancellation. But if you want a linear receiver, then you go with the MMSE and you know. Any question? Architecture for? I think the architecture is yeah, SIG is more complex. This is a kind of architecture. Yeah. Yeah. So I don't have that slide. Sure. Any other question? Mm. Yeah, yeah, of course. Yeah, I mean, if we, I think that's, if you want a less complex and reasonable good performance, we'll go with MMSE, okay? But if you go with good performance and if you are ready to sacrifice complexity, we had to go with the MMSE receiver. But in the 5G, we use MIMO and MRC. This guy, MRC is the one. Match filter is the very, very less complex receiver. You multiply the received signal with the channel coefficient complex conjugate and divide by magnitude. So this guy is the very, very less complex receiver compared to all of them because here you need to invert a big matrix here. You need to invert the matrix here for zero forcing, and MMSE, you need to invert the matrix, okay? So here, MRC here, you don't need to invert any matrix, just a multiplication. So the beauty of MIMO, if you do a maximum ratio combining, it will give you a reasonably good performance because of the large number of array. And at the receiver, for the uplink, the base station will do a maximum ratio combining. For the downlink, the base station will do a maximum ratio transmission, MRT. It will do MRT, maximum ratio transmission, which is a kind of a transmit beamforming because base station assume channel knowledge and it will do maximum ratio transmission. So these maximum ratio combining at the receiver, maximum ratio combining at the transmitter is the less complex to all of these things. That is what your MIMO is doing in the 5G NR. Any question?
In terms of other parameters also, MMSC, SIC is good.
Yeah. Obviously, it's good. Yes. As a receiver, MMSC SIC is the optimum, is achieved capacity. Similarly, there is at the transmitter you can do a similar concept. It's called dirty paper coding. I don't know you heard about it. That is the pre-coding techniques. Again, a nonlinear pre-coding techniques. So it's as I said, maximum ratio combining at the receiver, maximum ratio transmitter at the transmitter is a very less complex. And similarly, maximum ratio MMSC with the SIC at the receiver performing optimum at the receiver. Similar to this, you can do one transmitter pre-coding. It is called dirty paper coding. That is you do at the transmitter to get the full capacity. Again, dirty paper coding is a very complex techniques as well. So people don't use MMSC, SIC, and dirty paper coding, etc. Because of the complexity.
And with the 6G phones having market failing satellite links and all.
Sorry?
In the 6G phones,
Yeah.
receivers,
Yeah.
We have connectivity to satellite links also.
Yeah.
In that case also, the SIG might be very costly.
Yeah, very costly. You have to go with MRC, MRT. Yeah. So this is the theory. And we know how to realize the capacity, etc. But when you implement MRC and MRT, we know it is not performing to the capacity limit, but it's a trade-off between complexity and the performance. Okay, so we will be seeing the pre-coding in later on. Oh yeah. So we have a zero forcing receiver, and we also have a zero forcing precoder as well. Okay, we have a MRC precoder receiver. We can do a MRT. This is a precoder at the transmitter. These are will do. Okay, so if I delete this guy, these are the receiver. These are the transmitter. You do zero forcing precoder, MRT. And you can also do MMSC precoder as well. And corresponding precoder is called dirty paper coding. Dirty paper coding. Okay, dirty paper. Okay, so now I'm going to talk about fast fading versus slow fading. Okay, so this is another important stuff. So whatever the VBLAS, vertical bell laboratory layer space architecture that I started with today morning, it is assuming a fast fading channel between transmitter and receiver. We have a fast fading channel. We have enough diversities there because the channel is fast faded. Okay, but what happened if the channel is not fast faded? Okay, what happened if the channel is not fast faded? Then we cannot do a VBLAS architecture. We need another architecture called diagonal blast. Okay, so that's what I'm going to talk about now. Okay, so fast versus slow fading channel. So far we have focused on the fast fading scenario. So that means this channel is fast fading. So it have many channel realization is there. So that means your information, your data stream will go through independently faded channels because it's a fast fading channel. So you will get a diversity as well. So, but if this channel is very slow fading, we cannot do a VBLAS architecture. In that case, we need a different, okay? So that's what it's saying. So far we have focused on the fast fading scenario. Can VBLAST achieve the outage capacity of the slow fading channel? I said, yesterday, the fast fading channel, the information theoretic measure is the ergodic capacity or the mean capacity. But the slow fading channel, the information theoretic measure is the outage capacity or outage probability. The question is, can VBLAS achieve the outage capacity of the slow fading channel? The answer is no, it cannot achieve the transmit diversity. In the fast fading channel, the transmit diversity is not important since there is already a plenty of time diversity. Because in the fast fading channel, the channel is very changing dramatically. Your coherent time is very small. So your entire stream will go through different coherent time, and you will have a lot of time diversity. Okay, you already have plenty of time diversity. But in the slow fading channel, your channels are constant for a long time. The coherent time is large. So you won't get plenty of time diversity. In that case, you need a transmit diversity. So the VBLAS is not going to give you a transmit diversity. In that case, you need a different architecture. So that is called diagonal blast. Okay, in slow fading channel, there's no time diversity, so coding across transmit antenna become important. So we are going to talk about coding across transmit antenna. Okay, so challenge is to combine the SIG. So we are going to do a coding across the transmit antenna, and also we need to combine with the successive interference cancellation, SIG. So that's what we are going to look at. It's called DBLAS architecture. So I will explain to you what is the DBLAS architecture next. So the DBLAS architecture, easy to explain with the two transmit antenna, let's see. Okay, so what's the so this channel slow fading channel mean this channel, let's say this channel H1, which is contain H11, H21, H11, H21, and then this channel H2 vector is H21, H22, H12. So your channel is H1 and H2. So this is your channel. Okay. So what is the what we are going to do in the D-BLAST, because these channel vectors H1 and H2 are going to be slow fading mean they are going to keep constant for longer period. So your coherent time is large. Okay. So it's going to stay longer period. So what we had to do is D-BLAST mean your stream is going through half of the stream go through first antenna, the half of the stream go through the second antenna. So that means half of the stream is going through the H1 and half of the stream is going through the H2 channel. So that's what is called diagonal blast, because your stream is going to, not all the stream is going to through the one antenna, half of the stream go through one antenna and half of the stream go through the other antenna. So what will happen is at first kind of a time slot, n time, let's say this is the n, okay? And so first n time, what happened is this guy will go, this guy will go. So go through the second antenna. So this is going to be this stream. So entire stream I divided by, this is the first stream, the superscript saying the first stream, and then A, B part, two part, A part and B part. This is the second stream, the superscript denoted second stream. This is A part and the B part. So at first n time slot, you will send the first stream, half of the first stream, and this guy is not going to send anything. So this first antenna is not going to send anything. So this guy is sending, the second antenna sending this stream, okay? The second n time, what happened is, this guy, this second stream will go through this antenna, so XB1, and then this first stream will go through this antenna, okay? So this is XA2, okay? So you will see the old stream, okay? So let me write it here, XA1, XB1, and this is like that. So your stream, the first stream will go through the first and second antenna. The second stream, the half of the first stream is going through the first antenna. So what I'm saying is your entire stream is going through, half of them is going to one antenna, half of them going to the second antenna. So that's why it is called D-BLAST, okay, diagonal blast, okay. So what happened is, similarly you will repeat, okay. This guy is, stream goes, the first part of this stream is going here, the second part will go here. Goes like that, it will continue, okay? So you see diagonal, okay, the streams are going diagonally. So what we are trying to do is, half of the stream goes through H1, half of the stream goes through H2. So we are getting a diversity. We wanted to send the old stream through different channel, mean we will get a diversity. So that is the objective of D-BLAST. So you first receive from the this stream, okay? So you first receive, at the receiver, for the first n time slot, you will receive this guy. There's no interference because first antenna is not transmitting. You can easily receive this one, okay? You can easily receive that. Then what happens is you receive second stream, second n time slot, you will have both antenna is transmitting, but you estimate this one, you estimate this guy, okay? You estimate this guy, and then subtract from this portion, and you estimate this one. So you receive this one without problem because there's no interference. Then you receive this guy, okay? And then you subtract this guy, and then you estimate this one. So that's what they say. You estimate this guy, which is the G stream, and then you subtract that stream from the receive signal, then you estimate this guy. So you had to do a SIC receiver. Then you cancel the interference, and you receive this guy. So similarly, you continue, etc. So what this is doing is the D-BLAS architecture, D-BLAS convert the MIMO channel into a parallel channel, and a good time diversity code. Time diversity code mean your LDPC code or turbo code can use to conjunction with the D-BLAS to achieve a good outage performance. So I hope you understand what is this D-BLAS is doing, because the channel, this is for the slow fading channel. Slow fading channel, this channel is constant for longer time. So your coherent time is very, very large. So there's no plenty of time diversity. If it is fast fading channel, your big stream, the entire stream will go through different coherent time. You will get plenty of diversity, time diversity. But in the slow fading channel, your stream won't go through this time, channel is not going to change much, so you won't get the plenty of time diversity. So you need to get a different kind of diversity. How do we get different diversity? You split the data stream and send across antenna. So by doing so, your entire stream is going through, first half of the portion will go through H1, and the second half of the portion will go through H2, and so you will get a diversity. So that's what is about D-BLAS. So D-BLAS, with the successive interference cancellation, we will be able to get a good performance in the slow fading case. Any question? Maybe we'll take a break. If you have any question, please ask me.
You are getting tired, sir.
No. I think 1 hour is the maximum we can talk, isn't it? So we started. Yeah.
Yeah, please sit, sir.
No. Any question we can discuss? So next, after the break, I will talk about multi-user MIMO downlink linear precoder.
Yeah, if you are having any doubts, please ask.
Okay, so that's what I explained yesterday. Oh, no. Okay, here, okay. So this is the channel capacity, MIMO channel capacity, okay. So as I said, this channel between the transmitter and receiver are random, okay. This guy is random. This channel H matrix is random variable, okay. So this guy is random variable. So log determinant in the capacities, this is the log determinant capacity, this is equal to C capacity, also random variable. Because this guy is random, so the C, this is a matrix random variable, but the C is a scalar, that is a random variable, okay? So when you take the expectation of that random variable, we talk about ergodic capacity or mean capacity. So that is the information theoretic measure for fast fading channel. Fast fading channel, we take the expectation of this capacity, mean capacity or ergodic capacity. But the slow fading case, we took the information theoretic measure, outage probability and outage capacity. So what is that meaning is, So it's a slow fading channel. So and channel will take a one realization and stay constant for a long time for the slow fading channel. So you assume this channel can support, let's say, R bits per second per hertz, okay? You design a communication system accordingly. But let's say your channel is in very, very deep fade, and it won't support that R bits per second, then you are in outage. You are in outage because you design a communication system saying my system is going to support this R bits per second, but this H is very random and it become a deep fade, and then the capacity of that channel in the case of deep fade is not going to support that you are R, that you are in the outage. Okay? So what is the probability of that event is going to be outage probability. Okay? So if you are given outage probability, let's say this is like a 0.01 or 0.01, let's say, mean you are taking 100 realization of the channel, one of them is outage, so 0.001, okay, 0.01, okay? So 100 realization of the channel you take, one of them is outage, so 0.01. So you put the outage probability 0.01 here and try to find the R using this equation. That is outage capacity, okay? Given outage probability, you go and find the R, that is outage capacity. So if you given R, the probability of happening that event is outage, okay? So if you are talking about slow fading channel, this is your information theoretic measure, outage probability and outage capacity. Any other question? Okay.
T did not comment. Yeah, please wait for 5 minutes. By the way, everyone signed in the attendance sheet, huh? Can you share the yesterday's papers?
Yeah.
Yes, sir, I forgot to ask.
Yeah, I know.
Please say, yeah, yesterday's code also, sir.
The code is in the laptop.
Which laptop?
Laptop I use.
Yeah, Mubina's laptop. Okay.
Yeah. It is in the downloads file.
In the download.
Download folder, yeah.
Yeah, I have to ask. Huh? Yeah? Okay.
It is in the download folder.
Yeah, I will send. In the downloads folder, you there? Yeah, then I will send you. Yeah, please send today's slides and yesterday's slides.
Yeah, sure.
Which architecture was implemented in real-time 5G case?
Sorry?
Which architecture was implemented for 5G?
Yeah, 5G is, we use MIMO, and we use maximum ratio combining our maximum ratio transmission. This VBLAST is a kind of a MIMO architecture. It is implemented in the Wi-Fi system, etc. Yeah. Yeah, VBLAST. Yeah. Wi-Fi, yes. Yeah. If it is a slow fading channel, your channel between the access point and you are not moving much, so it is going to be D-BLAST architecture will be.
Which one is more expensive? These
Yeah. I mean, MMSC is more complex. Zero forcing is not much complex. So order of complexity is MRC is less complex, maximum ratio combining, and then zero forcing is second, and MMSC. And then MMSC SIG this is a non-linear receiver. So the complexity is increased like this. So this is the nice proof. Maybe we'll do a question later on. This, how do we prove this one is? This is a nice proof. Yeah. Any other question?
Sir, you got what you go ask recorder. Recorder, sir.
Precoder we are going to study in a minute. Okay. So this is what we are going to see, linear precoders, and then we'll do that question maybe today morning. You know, the CMO channel, MISO channel, and then MIMO system, you know, we see the capacity analysis and the receive architecture, etc. Now we are going to put all these together in the cellular context, okay, cellular system context. So the story now is multi-user MIMO, downlink linear precoding. Okay, so that's the one. So this one lead to messy MIMO. Maybe probably we'll talk tomorrow morning about that. But now we talk about multi-user MIMO, downlink precoding. So here, you know, we are talking about single cell here, single cell. There's a base station here with the multiple antenna and mobile unit. There are K users, let's say. The base station send a waveform that contain all user information. It will transmit to a downlink system users, and each of these users will extract its own information. Okay? So let's see if the base station is sending information to all of these users, but this user is not interested in any of the other user information. He is only interested to listen, receive his own information. Okay, okay. But so if the base station is going to send normally one waveform which include all the user information, but this guy is only interested in his own information. Okay, so other user signals are going to be interferent to him. Okay. Okay, so that is called multiple access interference because each user receive all user data. So that is called multiple access interference. So to avoid that interference, the base station will do a pre-coding techniques. Okay, okay. So that's the one we are going to see. It will do a zero forcing precoder or MMSC precoder. Okay. That's what we are going to see, zero forcing and MMSC precoder. So MMSC and zero forcing concept is done at the receiver side, and you can do at the transmitter side as well. So we are going to look at it, the zero forcing precoder and MMSC precoder at the transmitter side. That's what the morning session is about, the receiver side signal processing. Now we are talking about the transmitter side signal processing. So in that case, we say precoder rather than the receiver architecture. Okay, we say precoder. So, but this base station will do. It can do a zero forcing precoder or MMSC precoder. I will tell you what is this. How do we do that? If we do that, this guy will receive his own information only. It won't receive other information. So each of the user will receive its own information only if we do zero forcing precoder or MMSC precoder. And there's another one called MRT, maximum ratio transmission. This is the one is happening in the 5G and R with the you know, messy MIMO case. Okay, so this slide set is not for messy MIMO. We will talk messy MIMO later on. So in the 5G and R messy MIMO, we only do MRT, maximum ratio transmission is good enough. Okay. Anyway, So the story is, if the mobile base station send all the user information, this guy will receive all the user information. So that is causing interference. That interference is called multiple access interference. So to avoid that interference, this guy only wanted to receive his own information. Okay, so all the user information is coming here, but this guy wanted to get his own information and don't want to receive other user information. So this guy had to do interference cancellation, etc. So that will cause a lot of complexity to the mobile unit. So we don't want mobile unit to do a lot of signal processing. So that's why we do a pre-coding at the base station. All the complexity will transfer to pre-coding at the base station, and this guy will do a simple receiver. Then only your mobile phone will last for a long time. Okay, so that's why all the complexity is moved to base station, and we don't do any signal processing at the mobile unit. So that's the story about pre-coder. Okay. So this is the kind of a downlink processing. You have a binary data. So let's say the base station wanted to send some information to image or video. It is first change it to binary and then do a modulation and then do a pre-coding. That's what we are going to see, pre-coding. The base station will do a pre-coding and send it through the channel, and then your mobile unit will receive and then demodulate the information that you send here. Okay? So here, the precoder, to do a pre-coding at the base station, you need to know the channel state information at the transmitter. TCSI mean channel state information at the transmitter. To do pre-coding, we need a channel state information. At the receiver also, receiver channel state information, etc., etc. So we need a channel estimation. So in general, precoder requires channel state information at the transmitter. Okay, so that's big asking. I told you the transmitter know the channel is a big assumption. Okay, receiver know the channel is okay. That's what happening in your 3G, 4G, 5G phones. But transmitter also know the channel is you are asking more. Okay, this is achieved by channel estimation and the feedback. So transmitter know the channel can be achieved by channel estimation and the precoder at the feedback. Okay, so yesterday I mentioned there are two modes of operation. One is called frequency division duplexing. Other one is called time division duplexing. Okay, so frequency and time division duplexing is called FDD and TDD transmission mode. Okay, so what does FDD mean? Okay, so here's the base station. Here's the user downlink user here. FDD mean uplink and the downlink are using a different frequency. Okay, uplink use different frequency, downlink use different frequency. So this is called FDD. Okay, so you have Airtel buy a frequency from the government, then half of the frequency is used for downlink and half of the frequency is used for uplink. Okay, so that is the FDD. Frequency division duplexing. In the frequency division duplexing, the base station will send the pilot signal to the user, and then user will estimate the channel and then feedback the channel to base station. Then only the base station can do pre-coding. Okay, so because the uplink and downlink are different frequency, so the channel will be different as well. So here, base station and mobile unit transmit on a different frequency. They are different frequency. Uplink and downlink channels are uncorrelated. Because they are different frequency, these channel, downlink channel and uplink channel are different. So to do downlink pre-coding, this guy need to know this channel. But this guy does not know the channel. What they do is send the pilot signal and this guy estimate the channel and then feedback. Then only it can do a pre-coding. Pre-coding need a channel knowledge. Okay? But because this channel is different than this channel, so that's why this guy have to estimate and feedback. Okay, so this channel and this channels are different frequency. They are uncorrelated. Okay, mobile unit need to estimate the downlink channel and feedback to base station. Feedback to base station. So this is a big resources consuming process, okay? So up to 3G and 4G, our system are FDD system, okay? And up to 3G and 4G systems are FDD system. We do TDD system also there, but mainly FDD system, so we spend more time on channel estimation and feedback, okay? Okay. But, okay, let me tell you about TDD system. So TDD means time division duplexing. So the same frequency is used for uplink and downlink, okay? So this is called TDD, but different time, okay? This portion of the same frequency is used for uplink and downlink. This portion of the time for uplink, this portion of the time for downlink, this portion of the time for uplink, etc. So this is called TDD system, okay? So this is base station and mobile unit transmit on the same frequency. Uplink and downlink channels are correlated. Base station can accurately estimate the downlink channel during the uplink reception, okay? So what this is saying is, here is the same frequency, uplink is, downlink is happening. So in the uplink, the mobile unit send the pilot signal, so this guy can estimate the channel. So that channel is same for downlink as well, because same frequency, okay? So this is called channel reciprocity, okay? So in TDD system, we have a channel reciprocity. Uplink and downlink are same frequency. So this guy don't need to estimate the channel and feedback, because during this training, this guy will estimate the channel. So same channel for downlink as well, because the same frequency, okay? So this is called channel reciprocity. So TDD is very famous in 5GNR, because in 5GNR, we have a large number of antenna, okay, massive MIMO here, okay, 64 antenna or 128 antennas are here. So each of the antennas, if we have large antennas, we have a lot of channel coefficient to estimate, okay, because we have large antennas, okay, massive MIMO here, 64 antennas. The user have a single antenna. There are a lot of channel coefficient to estimate, okay, 1H2 up to 64 channel coefficient to estimate, and feedback, then you don't have the coherent time, you will estimate the channel and feedback, your channel is changed. So you don't have a time to do data transmission. So that's why there's no FDD massive MIMO base station deployed in the 5GNR so far. Their FDD system is not there in the 5GNR, okay? So 5GNR, all the base stations are TDD, time division duplexing, okay? Because if it is massive MIMO, this guy will spend a lot of time. The coherent time is the time channel is constant, okay? Coherent time is the TC, is the channel is constant. He will spend a lot of time to estimate the channel all this time, because there are so many channel coefficients. Then he had to spend some time to feedback. By the time channel change to different realization, so FDD system is not going to work, not successful so far in the massive MIMO case, okay? So, but up to 4G, we don't have a massive MIMO system. We have only 4 or 8 antennas, so we can do a FDD system successfully, okay? Any question? Okay? So that's the beauty of TDD. You have a channel reciprocity. Uplink and downlink is a same channel. So in the uplink communication, this guy will estimate the channel. That channel is same for downlink, so he can do a pre-coding. So pre-coding need a channel state information at the base station. So, okay, so now I'm going to talk about pre-coder, okay? So MIMO linear pre-coding, when employing receiver-based detection, multi-user detection causes significant computation burden for the mobile unit. So as I said, if you send all the user information, this guy had to decode his own information and cancel all other user information. This guy will spend a lot of signal processing power. So in order to avoid that, we transfer everything to base station. That's what this slide is saying. So mobile unit need to do channel estimation, We employed transmitter-based pre-coding, all the signal processing done at the base station, less complex, mobile unit have a less complex, simple and cheap mobile body unit, okay? So this is, I already told you, all the signal processing is done here, and this guy don't do much signal processing that will lead to your battery will last for a long time, okay? So what is happening here, okay? So this is the MIMO channel. You can consider, we are considering a downlink scenario, but not massive MIMO. So let's say this guy have a 8 antenna or something like that, okay? Up to 8 antenna. So there are 4 users or something like that. Let's say 4 users. Okay, so this is, let's say, M antenna and K users. Let's say, normally assume M is larger than K. And even though these users are geographically different location, but you can, for the time being, for the modeling, we assume these guys as a kind of a co-located. So the channel is going to be between here to here is K into M MIMO channel, okay? Even though these users are different location, you can put all these users as a co-located places, then you can model the downlink channel as a K into M channel matrix. So that's what is shown here. This is the base station, have a multiple antenna. This is the receiver. Each of these antennas are considered as one of the users' antenna. Anyway, so we can still consider this is as a MIMO channel, okay? Increased capacity and transmission rate by use of spatial multiplexing, we saw that. Improved performance due to diversity, spatial diversity, interference between, okay? So interference between channel antennas as well. So the received signal here can be written as this equation here. So this is the desired signal for the kth user. He is interested in his own information, desired signal. All other other user information from the downlink user, base station to others are considered as a interference. Okay, so now we need to do a pre-coding. So let's say this guy wanted to transmit all the user information is X. Let's say all the user information is X. It is going to multiply this X by a matrix called T. This is the matrix is called precoder. We will see what is that precoder is going to be. So it's given here for the zero forcing case. This is the precoder. So so we say the base station wanted to send all information X contain all the user information. Before sending that information, this guy multiplied by a matrix. That is a called precoder. So to do that precoder, you can see that precoder is turned out to be like this. It need a channel knowledge. This channel knowledge had to be known. So that's why, FDD system, all the users estimate the channel and feedback, and TDD system, the channel is channel reciprocity is there. Anyway, so we are going to find what is the T such that each of the user will receive their own information only. They are not going to receive other user information. So this is called pre-coding, okay? So let's see. Matrix representation of the MIMO downlink receive signal. Receive signal is H index plus Z, okay? So this receive signal is all the user receive signal are put together as a vector, okay? This receive signal is all the user signals are put together as a vector R, and H, X plus Z, okay? So what is the matrix T that minimize the mean square error of the receiver? So we wanted to find, we wanted to find a T matrix that minimize the R minus X, okay? We wanted to find a T. It turned out to be this optimization problem have the T matrix that is the zero forcing precoder here, okay? Zero forcing precoder here. So there is some scaling factor that will come, but we will talk about that later. So this is the zero forcing precoder that we saw similar to the zero forcing receiver that we saw earlier. So this is a zero forcing precoder. So the X is multiplied by T. That T guy is this one. Okay, you can see it involves channel. That's why we need a channel knowledge here. So if you do that, each of these user will get his own information only. Okay. So you can see this is the receive signal. This is the precoder T, X, H, and you can see the T is this guy. This is the T. Okay, this is the T. You remember the T is this guy, H Hermitian, H into H Hermitian inverse. This is the T, the precoder, zero forcing precoder. So the receive signal is, there is some scaling factor F, don't worry about that for the time being. H into the transmitted signal is Tx. This is the one transmitted signal. But now we know T is this. We know T is this. And if you see this one, this into this is identity matrix, and you will get this. So each of the receiver will get his own information. Okay, each of these. This is a receiver is a R. R is a vector contain each of the user information. R1, R2, up to Rk is put as a vector R1, R2, up to Rk. So each of the user will receive his own information, and because of the precoder, okay, hex, okay. So this is all about precoder. This is the MMS zero forcing precoder. No interference, single antenna perform for every single antenna performance for every antenna. However, the power of the desired signal is reduced due to factor F. This power reduction can be big, depends on the condition of. Okay, so there's because of this inverse, this H matrix had to be good channel. Okay, in other words, there should be a risk scattering between transmitter and receiver. Otherwise, if this guy become a ill-conditioned matrix, then inverse will give you some trouble as well. Okay, so if you have a rich scattering between transmitter and receiver, then this condition number of this channel matrix is good, is very close to 1, and then you don't have any problem with the inverse. Okay, so this is called zero forcing precoder. It is also called channel inversion precoder. Okay, there are many names. Okay, so it's the same as channel inversion precoder. Okay, so there's another precoder is called it's similar to regular MMSC precoder. Okay, it's called regularized channel inversion. There's an additional term here, alpha into I. So this is the MMSC precoder. Zero forcing precoder, and this is a zero forcing precoder. And if you have, we are talking about regularized zero forcing, regularized channel inversion, or MMSC precoder is going to be some alpha into I will come here. Okay, so that's the difference here. So this is again turn out to be it's going to perform better because this channel inversion will be won't be an issue here because alpha into I. So the alpha can be, we can optimize the alpha such that it is increase the capacity or something like that. The alpha depends on does not guarantee a. Okay, so the scaling and all these things, the inversion problem will be eliminated by this alpha here. Okay. Any question? Yeah. No, not that. Okay. Or get their own information. Yes, that's what we prove here. You see here, because of this become identity, the receiver signal R1 is X1. Yeah, multiple is the case. Yeah, it's downlink. Any other question? So up to 4G, we use this kind of FDD system, frequency division duplexing, do channel feedback, and do this kind of recorders. Okay, so here some performance curve. This is the simple error rate versus SNR. Okay, so there are two set of results here. One is the here is the 4 transmit antenna and 4 user. Other one is 10 transmit antenna and 10 receive antenna, 10 users. Okay, so you can see this one is for the 10 transmit antenna and 10 receive antenna, so 10 users for the regularized inversion, channel inversion precoder, and similar case for the channel inversion precoder is there. Okay, so these two curves are for 10 antennas. Okay, these two curves are for 10 antennas. This is regularized channel inversion. This is zero forcing or channel inversion precoder. You can see this regularized channel inversion precoder performance increase, okay, improved. And these two curves are for 4 transmit antenna at the base station, 4 user at the 4 downlink users, and this is for the regularized precoder, and this is for the channel inversion precoder. So there is a performance different compared to channel inversion and the regularized precoder. Okay, any better performance? Yes, yeah, because of you know, all these gain will come, diversity gain, multiplexing gain, all these gain will come, and we will get performance improvement. This is for the bit simple error rate. I will show you some capacity plot here. You can see this is the capacity. Okay, so this is the you know, still we are far away from, okay, so I'll tell you what, so this is the kind of a channel capacity, some capacity, okay, channel capacity or some capacity. And this is the capacity for the regularized inversion channel precoder, and this is the capacity for the channel inversion precoder, okay. You can see, you know, the regularization precoder is performing better compared to channel inversion precoder, but still there is a gap here. This gap can be closed by using dirty paper coding that I mentioned, okay. Dirty paper coding is similar to MMSE SIG, MMSE SIG. MMSE SIG we do at the receiver side. Similarly, similar to that in the precoder we call dirty paper coding. If you do that, you will go closer to this line. Okay, but this dirty paper coding is very complex. You know, people have studied recently because of after machine learning, you know, research. People are doing studied how to implement dirty paper coding using machine learning techniques. So that's one paper by Madhani as well. Okay, so any other question? Yeah. Yeah. Okay. You want to note down or you want to see it? Explain. Any other question? So the TDD, FDD, you guys are happy? Yeah. Yeah. They can change the location, no problem. Yeah. Okay. So every core. Yeah. Yeah. So these results are for one coherent time. You know, one coherent time, the channel is constant, and all the performance is done like that. Yeah, one coherent time we had to do channel estimation, feedback, and transmission, and another coherent time. Yeah. The coherent time are still long enough to do all these things, even though the users are moving. Channel is not that much moved very quickly. So there is a coherent time to do all these channel estimation, feedback, and the communication. So, so this is the story. You know, single input, multiple output, multiple input, single output, then MIMO, you know, point-to-point system, then multi-user MIMO like this, and then messy MIMO. So this is the way the story, you know, evolved. Okay, so 2G and things like that, we use two antenna base station. And we did a receiver beamforming, etc., transmit beamforming, 3G as well, space-time block code. And then the MIMO point-to-point system came specifically for the Wi-Fi scenarios. Then that lead to, you know, multi-user MIMO in 4G, and then 5G become messy MIMO. Any other question? You want the next slide? Yeah.
So in RCA, it's regular standard version,
Yeah.
capacity as well as the performance
Improved. Yes.
improving
Yeah.
with increasing number of antennas.
Yes. Yes. Yes.
That is not the case in CA.
No, CI also going to be improved as well, but there is a performance gap. Yes. You can see. So here is M is equal to N. Antenna increase, the capacity increasing, but it's, as you can see, it's getting saturated, but normally increase. Yeah. So here is, this is for, yeah, you can see this is 10 users and 4 users. The performance will improve with the MIMO system because of the diversity and multiplexing trade-offs. Performance, yeah, gains. Any other question? Shall we do caching or MIMO? Huh? Okay, so we are planning to do something different now. Did you heard about edge caching? Edge caching, yeah. So what is edge caching is? I will give you a small introduction and then Navneet can present. Edge caching mean this is again a belong 5G research. Okay, belong 5G research. So. So whenever, you know, you have a base station here, users are here, let's say if there's some popular news came or popular video, movies are released, then if there's a popular news or popular video movies are released, each of the users will asynchronously download those news and the videos or movies, etc., etc. So the base station is connected to the core network here. Every time somebody requests the file, it had to go through backhaul through this core network and bringing to the base station and sending to this one. So every time user will request the same file, the popular file, again and again and again in a different times, then every time the base station had to go and get that file from the core network, some content distribution network or somewhere, and get it back and to deliver to the user. So people have seen this trend, and then this backhaul become very congested, very congested. So to avoid that, you know, in the future cellular network, if there is a popular file, people are asking, again, it depends on the time and the location on the areas. You know, the popular in, you know, something in here is not very popular in somewhere else. So it's all dynamically, the popularity and everything is changing. So the base station do some, prediction, etc., and take that file and cache that video in the base station. That's called edge caching. Okay, edge caching. This is the edge of the network. It is cached that content, video or whatever, and whenever these guys has a request, it won't go and get the file. It will have it here and serve the user. This is called edge caching. This is one of the research area recently. Is again a lot of research have been done how to predict at particular location and particular time what is the popular file, and then cache that file to serve the user. So something popular today may be not popular next tomorrow. So that's again machine learning techniques are used to predict those files and used to cache that one. So this is called edge caching to alleviate the backhaul congestion. Okay, so maybe Navneet is going to talk about some edge caching research happened in the recent years. I'll come back to tomorrow morning for the messy MIMO case. Okay. What do you want? Research.
So wireless edge caching is a part of 5th generation 5G. So what does it mean? Edge means, it means network edge. So for example, whenever you make a call or you download some video, so this is your mobile and it goes to some base station, and then base station is connected to another, and then we have routers are connected, and this is like the network of base station, and then we have content server. Okay, so this is the network. Okay, so edge means the network, the nodes that are directly connected to the users. Okay, if this base station is directly transmitting to this user, so this is called the edge node. Okay, so wireless edge caching means we are caching means storing. We are storing the content at the edge nodes, okay, and we are delivering it wirelessly. So this is the outline of the presentation. So here we are presenting the dynamic caching. So dynamic caching means dynamic caching means the popularity of files that we want to store in advance are changing. So how do we store it? That is dynamic caching. Okay. So we first present the motivation and introduction to dynamic caching, then followed by system model. Then we present online techniques, online popularity prediction and learning. So note that there are two techniques here. One is prediction based techniques and second is learning based technique. And